This is a Chapter 26 class example problem. It's a test of homogeneity. So what we have is we're given an experiment. So think of it as we take some subjects and we give them treatment 1, which in this case is a placebo, and treatment 2 is a natural remedy. It's called St. John's wort, actually. And in the third treatment is this Prosrex, something like that, which is actually, I believe it's a drug, or it's certainly, I don't know if it's, I don't know clinically if it's a drug, but it's certainly something that was created. It's not, it doesn't come from nature. So, of course, we would do a random assignment. And I have no idea, but they don't show replication. But we know the total. We could probably find the total. I didn't add them up, but there's a total. So we would assume that there's sort of some replication. Let's see. This would be, oh, it's 30. So the total is 90. So it's 30, right? Each group got 30, had 30 people. Now what we're doing is when we analyze the results at the back end and we look at the response, we're asking, did their depression return, or did it go away or not return? Okay, so you have to look kind of closely, but certainly we have counted data, right? We have counted data for one variable, one categorical variable. That's the critical point here. Categorical. Variable. Now, what we happen to have, though, is we have two groups. When we have one variable. So in this kind of test, we want to do a test of homogeneity, and what we're looking for is to see if the two groups are the same. Okay, so for these kinds of tests, we always assume they're the same, and then try to prove that they're not the same. Okay, so I always make that little note to myself. So if I was going to say they were the same, I would say something like the rate, can't spell today, the rate of depression recurrence is the same for all three treatments. Okay, and so here we would just say the rate of depression recurrence is not the same for the three treatments. Okay, so that's how you would do that. So independence. Here, what we need to, since it's an experiment, we sort of have an exception. And I don't know, do they actually say treatments, the subjects were randomly, yes they do, randomly divided. So they used random assignment of treatments Okay, so that's good. Now the expected cell count. The way to get the expected cell count is you want to go, let's see, second matrix, and go in and edit matrix A, and you want it, we have 2 rows, so it's going to be a 2 by 3. Okay, rows come first, then columns. Okay, do that, then put the data in, go back to second matrix. Oh, I think if you hit enter, you can just enter the data. So enter the data. Okay, then do stat, test, and select chi-squared test, and just hit calculate. Make sure that you select that that A is the input and B is the output. That's the safest. Okay, so once that's done, then go back to second matrix, and this time select, don't edit, select matrix B, and look at the expected values, because they'll be in matrix B. Okay, and it's best to record them somehow, some way. So here they left us some room, so I'm just going to put them in. It turns out that it's pretty easy for this one. It's 20, 20, and 20, and then 10, 10, and 10. Okay, so the first thing that you want to just make note of is that all cell counts expected, don't say cell counts, say expected cell counts. I almost fell for the trap. All expected, can't write today. All expected cell counts are greater than or equal to 5. Okay, so now our conditions are met. Satisfied, so we will proceed with a test of homogeneity. Okay, and again, the reason we're doing homogeneity instead of independence is we only have one variable and 2 groups. If it was 2 variables in one group, then it would be independence. So test of homogeneity, and we're going to use a chi-squared model with the degrees of freedom. Let's see, it's row minus 1 and column minus 1. So what is that? That's there's 2 rows and 3 columns. So that's going to be 2 degrees of freedom. Okay, so when maybe you already recorded this, but you would do second. Geez, I keep doing that. It's not second, it's stat. Stat, test, and select chi-squared test. Make sure that it has A and B in it for the input and the output, and then hit draw. Okay, and then what you should get is you should get a chi-squared value of 8.4. Okay, and the p-value, that's the probability of the chi-squared value being greater than 8.4, and that's going to be 0.015. Okay, and if we drew the picture, it's not going to be that interesting. The curve, it's important, don't draw a curve like this, because that would be with a chi-squared value that's a little bit bigger. Okay, our chi-square value is very small, so it's more of a curve like that. Okay, but because the p-value is so small, you hardly want to shade anything at all. Okay, so our chi-squared value is 8.4. Here is 0. We're a long ways away from 0. A long ways away from the hypothesized value. Essentially, when we said they're the same, we don't use a parameter, but we're sort of suggesting that the value is 0. Okay, so as a minimum, you have to write the formula squared and divided by the expected. Now, if you just want to do that and put 8.4, make sure you go up here and you say something like observed values, so the reader knows that you know what you're doing, and then put in parentheses expected values. Okay, so that you've labeled what goes in here. I don't have a problem with writing it out. It doesn't take that long, and it just kind of helps me remember what I'm doing, where this chi-squared value comes from. So I just take every observed value and subtract it from the expected value, square it, divide by the expected value. So these are all going to be 10. And so I got 6 minus 10 squared divided by 10, 8 minus 10 squared, and 16 minus 10 squared. If you do this, write all this, and then for some reason you make a mistake, you'll probably still get full credit because they know it's just a calculator error. Okay, so in this case, the p-value is small. So we reject HO. Okay, the chi-square value is nowhere close to the hypothesized value. So there is strong evidence that, what do we want to say? That the rate of recurrence of depression is not the same for all three treatments. Okay, so that's great, but it's not very empowering. So there's one more thing you can do when you reject the null hypotheses. You might be able to go back and figure out what happened. So here, if you look closely, we want the depression, okay, to actually be lower. When depression returned, we want it to be lower, okay, if we have an effective remedy. Okay, so you can kind of see the 14 is lower, okay, and then we want no signs of depression. We want that to be higher, and we can see over here 16 is much higher than 10. Okay, so the way to really prove this out is you use what's called the standardized residuals, and here it's equal to the observed value minus the expected value divided by the expected value squared. I mean, all we're doing really is taking the square root of the component. Right here, we're taking the square root of this, and then we're calculating it for each term. What that does is each term will no longer be positive. Okay, so when you do that, here's what I get. I wrote it somewhere. I get 0.89 negative 2 Let's do this again. 0.89, negative 2.84, and let's see, 0.45, negative 1.34, and negative 0.63, and then finally 1.89. Okay, so what this tells us is that the dominant parameter right here was the placebo. So remember, to get the chi-squared value to sort of like not be 0. So if here's 0, okay, then each one of these terms, you start here and you just sort of add each term. So if we add a little bit for the first term, we add a little bit, but then this one's going to be kind of big, and then the next one's going to be real big, and then the next one's going to be reasonable size, and then another big one. Okay, so this is the biggest contributor, and you can see it's well below what we'd expect. But here what we see is that with this treatment, the recurrence of depression is much below what's expected, and then with this treatment, sort of like the non-recurrence of depression is much higher. So the standardized residuals suggest that people who take the prescription drug take Prozac are less likely to have their depression return than I guess taking nothing and or taking the natural remedy. St. John's Wort. Okay, so you can go a little bit further. That's the whole point. You can go a little bit further than making this general claim that they're just not the same. You can actually hone in a little bit and find the reason, or at least have a suggestion as to what aspect, what category of the variable led to a large chi-squared value, which led to rejecting the null hypotheses. Okay, that's how you do this problem. I hope that helps. Good luck.